Hey, welcome to part 2, vector valued functions. So for this example, we're given a vector valued function, 2 cosine ti minus sine tj. No, this is not a typo. We'll talk about that. And we want to take a look at this over the domain 0 to 2 pi. We're going to sketch the curve of this function. It says to start with parametric functions, but I'm going to start before that. Remember we talked about in part 1 that this is going to be a path on a surface. So, and in this case right here, it's a two-dimensional shape. So because there is no k here, this is only going to be two-dimensional. So we don't have to worry about a third variable in this one. So this is going to be a graph, two-dimensional graph, and in this case, because that's xy, on the xy plane. We're going to see a couple of examples later on what happens if we get off that xy plane. So when I'm graphing this, well, they're telling me that x is equal to 2 cosine of t and that y is equal to negative sine of t. So we're going to answer this question in just a few minutes. Well, what does that negative mean for us? Okay, so before we do that though, from pre-cal, we learned that to convert these, we can use our Pythagorean identity. Cosine squared of t plus sine squared of t equals 1. Well, what this is kind of telling me is that cosine of t is equal to x over 2. And that sine of t is equal to negative y. That's from my Pythagorean. So using my Pythagorean, then I can now write this equation as x squared over 4 plus y squared over 1 equals to 1. And hopefully we recognize that this is an ellipse right there. So if I sketch that ellipse, it's not too hard to do. X is 2, negative 2, 1, negative 1, not drawn to scale. And there it is. Now, but be careful, we're not quite done. We want to sketch a vector. Remember, vectors have direction. So we want to give the direction of our ellipse. Now, typically, the direction would be counterclockwise. But let's see what happens. How can we get direction? I look at my values, t, x, and y. Now, my t, if I let t be 0, my x comes from this 2 cosine t. Okay? Cosine of 0 is 1, so that becomes 2. Y, if I let t be 0, y becomes just 0. Sine of 0 is 0. So we're at the point 2, 0. So this is where we start. And now I'm going to let t be pi over 2. It's easy to handle. So at pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. But this is going to become a negative 1. So I'm down here. Notice the direction. It goes clockwise. So this goes clockwise in this case. And I got that by just plugging in my points, like you did in pre-cal. So what does this negative mean? This negative means that this will change the direction of the ellipse. Changes that orbit. So let's take a look at another example. We're not going to sketch this one. Don't worry about that. But we want to find the domain of this. Now remember, this is x, y, and z. So we have all three coordinates here. So this is a path on a surface, on a three-dimensional surface right here. So we want to find the domain. So remember what they're looking for, just like the one before on the first page, part 1 here. Not that one. Over here we want to find the domain. So notice the x, y, and z all depend on t. So x, y, and z depend on t. So I'm going to start with the x. Well, x is the square root of t. Well, that's pretty easy. So all my x's have to be greater than or equal to 0. Looking at the y's. Y is cosine of t. I can get rid of that t if I solve, right? So I know that this x equals the square root of t, therefore t is equal to x squared. So I can write y as cosine of x squared. Well, what can y be? Well, biggest cosine could be is 1, so y is going to be between negative 1 and 1. To look at the z's, this is a tough one. 1 over x squared minus 3. To do this one, I'm going to sketch it. Okay? There. Now, I know I have vertical asymptotes at negative root 3 and positive root 3, and my horizontal asymptote is 0 from pre-cal. If I pick a point, let x be 0, I get negative 1/3. That's the biggest it's going to be at the bottom, so it just goes down like here. These are both single asymptotes, multiplicity, so I know it's going to open up here and right there. So for z, I know z can be greater, let me start over here. Z has to be greater than 0, or z is going to be less than or equal to negative 1/3. Right here. I get it from my graph. That's pretty tough to do, but it's kind of fun. All right. The next example, here we have, now this is going to be very similar to example number 3 here. Here we have a 3-dimensional object. This is a 3D graph right here. The only difference is z is always going to be 1. Now they're telling us that x and y are part of the domain. Find what set of points represents the domain here. So from pre-cal, we would say x is, we know that this is going to become 3 sine of t, and that y is going to be the cosine of t. I can get the domain pretty easily from here. My x's, well, sine can never be bigger than 1, so that's going to become 3. Mostly going to be 3. So my x's are going to go from negative 3 to 3, where my y's are going to go from negative 1 to 1. Now notice, we typically let x be cosine and y be sine, but they switched it here. You don't have to, there's no really rule. We just use that that Pythagorean cosine squared plus sine squared, let cosine be x and sine be y. We just use that because it's an easy way to remember it. But there's no real rule that says x always has to be the cosine variable or y has to be the sine variable. We can switch them around. It will affect our vector, but we'll talk about that in just a moment. Right there. So there's our domains. Now they say, hopefully you guys recognize this, by the way, this is an ellipse, right? We know that this is an ellipse. So z is now my dependent variable. What's the range? Well, I get that from here. There's z. Well, z is just always 1. Right here. So let's graph this. What we have here is an ellipse. Okay? My x's go from 3 to negative 3. My y's go from 1 to negative 1. But we are raised up 1 unit. So you can kind of see our ellipse right there. There's our ellipse. So this is an ellipse raised up 1 unit right there. So let's talk about the direction of it. Let's see what switching your x and your y, if your sine and cosine, does to the graph. Start with t, x, y, z. Z is always going to be 1 here. Let t be 0. Sine of 0 is 0. Cosine of 0 is 1. So I'm starting at over here. That's where I'm starting this time. And let's see what here. If we go become pi over 2, sine of pi over 2 is 1, so we get 3, 0, of course that's 1. And we go here. So we get our direction. And again, this is going to be clockwise. So this changing the sine and cosine changes your start point, and it more importantly changes direction, because we can really start anywhere, but it changes our direction. Very easy to do. All right, let's take a look here. Now look, this almost looks the same as number 5, but we have this 2t right here. Well, what does that do for us? Well, this is going to be a circle. Hopefully we've kind of recognized if I have x equal to sine of t, y is equal to 2 cosine of t, this is a circle. But what does that 2t do? Now remember, this is my z value. So if I have my circle, what's going to happen is it's going to go around in a circle, but it's going to start to raise. As t increases, we're going to start to raise up. And what you wind up with, if we go back to our toilet paper roll of mathematics, what we wind up with is a spiral right here. So it's going to make a circle, but it's going to be lifting up as z is going to be increasing, as t increasing. So this is going to be a circle, and with the height changing as z increases. Think of it like a slinky. So it's a helix. This is what we call helix or spiral. We're going to see double helixes later on this year too, like you did in biology. Thank you, Watson and Crick. So if x and y are part of the domain, what set represents the domain of our graph? And that's easy. I can get my domain, again, just looking at my rule. Sine is never bigger than 1, so we're going to go from -2 to 2. And y is going to go from also -2 to 2. So there's our domain. If z is my dependent variable, what's the range going to be? Well, remember, z is this 2t. Z has no restrictions on it. It can be anything. So let's see what this would look like. Let's go ahead and graph this real quick. X, Y, Z, T. Remember, X is this 2 sine t, Y is 2 cosine t, Z is 2t. So 0, sine of t is 0, sine of cosine of 0 is 1, so we get 2, 0. So on the y value, I'm starting at 2. So there's I'm starting. That's where I'm starting. Ready? Go pi over 2. Okay, at pi over 2, we get 2, 0, be careful, pi, oh, wherever that is, pi. So I'm going to go, so here I'm at 2, but a pi. So you can kind of imagine this spiraling up there. And it's going to keep going. I'm not the best at drawing these. And you would get a spiral. And that's what our helix or our spiral would look like. But notice the direction it's going. We change sine and cosine. So again, this is going clockwise as it's spiraling up the ladder. Right there. All right, go to part 3. We'll finish this up. I'll see you guys then.